Bismillahirrahmanirrahim. Greetings. In this lecture, I'm going to wrap up the contents of previous lectures and make an intuitive definition of limit, and then come up with a rigorous mathematical definition of limit known as Epsilon-delta definition of limit. Now, as a side, I would like to mention that the Epsilon-delta definition of limit is part of the curriculum of Calculus 1. But most of the teachers, they do not cover it. And that was my case when I was in undergraduate. And one reason is that the definition is a bit abstract, and also the related terms and problems, and the instructors are fully aware of that, and because the students are taking calculus for the first time, they have difficulties with that. So they usually bypass it. So when I was in graduate school, that is the time that I was exposed to Epsilon-delta definition of limit, and I also found that most of, if not all of my classmates, we were in the same boat. They also did not know the definition, the Epsilon-delta definition of limit. That gave us a little bit difficulty. But anyhow, if you are going to be a mathematics major or an engineer major, you better master it now. You better master it now, you need it. And the definition itself, in its own right, has a fascinating application that we may talk about it. Okay, then let's get started, shall we? Now, as I said, I'm going to go, excuse me, as a review to go over the previous very quickly as a contents of the previous lectures. We started with Zeno's paradox. And Zeno's paradox was a fairy tale story we made, and that was the race between hare and the tortoise. And we found out that if the tortoise starts 1 unit length, whatever it is, whatever it could be, the fast-running hare could never catch the tortoise, theoretically. But in application, we know that is not the case. So that is exactly what the process of limit is. So theoretically, the limit is not going to be reached, but in application, it is reached. Then we went to a few examples. One of the examples we covered was that this one, that f of x equal to x squared over x squared minus 4 over x minus 2. Then we said what is the limit of f of x as x approaches 2. And we have heard that limit of quotient is quotient of limits. So we end up to be limit of numerator was 0 as x approaches 2. Limit of denominator was 0. So we came to the conclusion that limit does not exist. Because if limit exists, it's a real number, should be a number. So then as a good student of mathematics, we are not going to give up. We are going to approach the other way to see if really the limit does not exist. So instead of quotient, we changed it into product. X squared minus 4 over x minus 2, we wrote it in the form of x squared minus 4 times 1 over x minus 2. And then we took the limit. And we found out the limit again does not exist because we end up with a situation like 0 times infinity, which is nonsense. Because infinity is not a number. Like 0 times apple doesn't make sense. So we again become more kind of suspicious that limit may not exist. Then we went to a table, functional value table, and we made a table, and we found out that we were wrong. The limit does exist, and it is 4, in fact, with the numerical data that we got. And then we came to the algebraic manipulation and wrote it x squared minus 4 as x minus 2 times x plus 2, and over x minus 2, and we cancel x minus 2 by x minus 2. So we came up with another function, we call it g of x. And g of x was equal to x plus 2, then the limit of that as x approaches to 2 was equal to 4. So what we did for this one, we sketched the graph of g of x equal to x plus 2, and then we made a hole at 2, 4 in the graph, 2, 4. And that was the graph of this one. So that about that. Then we went for this one. So the limit of this exists. Now we came to x, absolute value of x minus 2 over x minus 2, and we investigate about the limit of that one. And when we came to that one, we came at, when we approach 2 from the right hand side, we end up to 1. And when we approach to 2 from left hand side, we end up to a negative 1. So if the limit exists, the limit must be a unique number, should be a number. So you cannot say it's 1 or negative 1 or flip a coin. So in that case, again, we concluded that the limit does not exist. But I have, let me say there is some side interesting I would like to mention. And this one is from the previous lecture. Now, look at that. From the right when we approach is 1, 1, 1. From the left, the approach is again negative, in this case is negative 1, negative 1, negative 1. But look at that, the function is perfectly defined to the right of 2, and perfectly defined to the left of 2, and also even including on 2, I put a dot here. But there is a big gap between them. So the kind of discontinuity, look at this one with respect to this one now. Now look at this one. Let me put it here. Now here, when we approach 2 from the right hand side and from left hand side, the function is perfectly defined, as you can see that. But the limit of that as x approaches to 2 from right and from left is equal to what? With the numerical data that we made, with the chart was equal to 4. But, but because x is never equal to 2, therefore, f of x will never be equal to 4, as the hare would have never catched the tortoise. Do you follow me? So here, because x cannot be 2, in this case, f of x cannot be 4 either. But we come back to that when we come to the continuity section of the calculus. But here I do mention a few words about that also. Now we have another kind. Now look at this one. I would like to compare this one with the previous one. This one to see the difference. Let me put it up again, maybe here, and then discuss it on. Hopefully it's not out of way home. Now, in this one, the limit from the right does exist. The limit from the left does exist, but these two were not same. So we say limit does not exist. Now look at this one. This one, let me bring it more toward these two comparison is important, that's what I put them there. So let me bring this one a little bit. Now here, when we cannot approach to C from left-hand side. Before we could, remember? Before we could, but here we cannot, because to the left, when we approach 0, the function is not defined, there is no graph, you can see that. So in this case, that there is nothing here, we can say that the limit does exist, but only from one side. One-sided limit, we call it. The other one, we could not say one-sided limit, because the function was defining both sides of what? Of 2. But in this case, the function is not defined to the left of C. So we can say, yes, the function, the limit does exist, and that is very important to mention when we come to the topic of continuity of a function. Okay, this was a kind of interesting to mention as a side kind. Now let me go to the next one that we have covered in previous lecture. This is just a short review so that we come to the intuitive definition of limit. Now here, the third one that we looked in the previous lecture was this example. 1 over x minus 2 quantity square, when again limit of that as x approaches 2. Now I selected 2 for all of them so that we can make a good comparison. Now this one, denominator is always positive, numerator is positive, therefore the graph we are expecting to be above the x-axis. But here, as x approaches to 2, the value of function keep going up. He doesn't give us any real number. He doesn't give 15, 20, 50 million. He doesn't give, he just keep going up. He keep going up from both directions. So in that case, we said the limit does not exist. Again, if limit exists, should be a number. But when we get closer and closer to 2, the function goes up and it doesn't give us any number. So we concluded that the limit does not exist. Okay, then we came to this example, limit of sine of 1 over x. And that was very interesting because it's a bit different. At the first glance, we thought that as x approaches 0, then 1 over x approaches infinity. So we immediately may come to the conclusion that limit does not exist. And as a matter of fact, when they give multiple choice, one of them is limit does not exist, and we look, x is approaching 0, we immediately come to the conclusion to select that one, limit does not exist, and we miss the correct answer. Okay, here, sine of x, as I have gone deeply into that in the previous lecture, is a bounded function. So that means no matter what the argument is, the sine can never be bigger than 1 or less than -1. And then approaching 0, we made a very good, smart selection to approach 0 through 2 over multiples of pi, 2 over k pi. We approached to 0 that way, and we found maximum, minimum 0, maximum, minimum 0, and so on. And when the closer we got to the 0, the more our sine of 1 over x started to oscillate. So it became very slippery. We couldn't catch it. When we go a little bit close to 0, it jumps to 1. So we say, okay, it can limit to be 1. When we went very little, tiny to the left of that towards 0, immediately jumped to -1. So it's just a slippery. We couldn't catch it. So we don't know. It doesn't let us to. It doesn't accumulate about 1 or -1. It doesn't let us to select any 1 even in between. So we had no choice to say limit does not exist. Do you follow me? But this is different kind of limit not existing than this, and this was different than this, and this one was different than this, and all of them are giving us the intuitive good idea to make intuitive definition for the limit. So let me see, I have it, yes. So let me hang it up for you, for those that they like to take notes. Sorry for the primitive equipment I have. I don't have access to a board. Okay. Okay, Rabbit. That fairy tale story of the hare and the turtle, the rabbit, give us a pretty good idea about the intuitive feeling of limit. Now I have written here intuitive definition of limit. Suppose that f of x is defined in an open interval a comma b. You remember the example I had? Let me bring it up. The open interval about c, it is to the right, but to the left the function is not defined. But he says let that to be defined, the function to be defined in the what open interval of ab that contains c except possibly at c. Then we say what? A real number L. So L is a real number, can be 0, can be negative, can be positive. as x approaches c, I like the arrow better, it's more kind of explicit, but most of the textbooks they put positive, means approaching from the right, negative means approaching to the left. Negative does not mean negative value or negative number, it means approaching to c from the left hand side. Then it says a real number L as x approaches c, we say that limit of f of x as x approaches c from right and from left is equal to L. By what? By constructing, we can do that also by constructing tables of functional values and graphs. They also help us to see what intuitive, we have done it in fact, what the intuitive feeling or approach of the limit means. Okay, then we have very good idea from all these examples from previous contents of those lectures we have covered we have very good feeling what the intuitive meaning of limit is. Now I think we are ready to go and look at the Epsilon-delta definition of limit, which is a little bit abstract and is kind of difficult for the beginners. And after I got this one, I'm going to go try to melt away the abstract part of the definition by paraphrasing the definition and also giving examples, and hopefully by the end of just this section, this lecture, hopefully we have overcome the abstract part of the definition. And when we go to the theorems and solve some problems, then hopefully 100% the abstract definition of the limit, the epsilon-delta definition of limit will be very explicit and appealing to us. We start to love it. Okay, now this definition was first given by Weierstrass. He was a German mathematician, and it's fascinating definition. It was late 19th century, and it has its own even application in its own right. It's a fascinating, again I repeat myself, definition, and because the entire calculus, the real and complex variable, sits on the concept of limit. So to have a rigorous and analytical mathematical definition of limit is very important. And we are really obliged and thanked to Weierstrass to coming with this definition. Now, this is, I read it for you, limit of f of x as x approaches c, always from both sides, equals to L. This notation means if and only if. This notation means for all epsilon given. Epsilon is a given. Epsilon like x, y, z is the Greek letters of alphabet. So for a given epsilon, for all epsilon, which means that makes epsilon to be arbitrary, there exists a delta, which means we can find such a delta such that x minus c less than delta, which means what? Which means all the numbers in a sense of delta tolerance to c. Delta tolerance to c, but not equal. X should not have the value of c greater than. Implies f of x minus L is less than delta. So please don't get discouraged. The definition is abstract. I already warned you about that. But with the patience and gradually, hopefully the abstraction will be filtered away. And this become very appealing to you. And the advantage of this in the textbook, this is almost about a line, less than a line long. And that we are talking already about how many, 4 or 5 sections, 4 or 5 lectures, and we have to use another 2 or 3 more lectures to fully comprehend just this definition. But once we finish with them, this definition will be very appealing, very sweet, and hopefully that will be the case. Okay, then I come here with 2 questions. Number 1 is that he says f of x minus L less than epsilon, but he doesn't say greater than 0. Why? We come back for that. And the other one, why does he say greater than 0 for this? He doesn't say it for this. That's second question. And the third question is that we say given epsilon, we determine a delta, which means delta will be a function of epsilon or could be a constant. So the delta will depend on the epsilon. If the epsilon change, the size of the delta will change. No, why not the other way around? Why not given delta we can determine an epsilon? That's a good question to ask. But when this kind of question comes to your curiosity, don't let that to interfere with mastering this one. Write it somewhere or put it on the corner of your head somewhere. And when you master this topic, this subject, then maybe on the way that you were trying to master this, your question has already been answered. But if it is not, then at that time, after you master this one, you look for your question. But it's good to ask question, but do not let that to interfere with what? With mastering the subject that you're is under consideration. Now, let's see, let me now try to, our goal is to paraphrase it and try to melt away the abstract part of this definition. And hopefully we will succeed, inshallah. Okay, Rabbit. Let's see what we can come up with. Now, this what I just had it in symbolic form, I'm putting in the word. It says limit of f of x is L if and only if given epsilon, which means epsilon is arbitrary. One can find a delta positive, so epsilon and delta both must be positive, such that what? Such that x minus e less than what? Less than delta greater than 0 implies f of x minus L less than epsilon. Now, the question that I asked already, I have written here for you. Why we say greater than 0 for this one? Why not just leave it alone? Just write absolute value. And why not also this one, we don't put 0 for that. Let's see if we can answer that one. Now, one thing I would like to mention is about very elementary basic algebra about absolute value. Again, we are doing our best to melt away the abstract part, even if we have to go to some topics in basic algebra. Now, one of them is this. This notation means what? This means x is positive, is that right? It's bigger than 0. This means x is negative. You see 0 is to the left of that, this arrow. So we don't want, the reason I brought that one up, because I don't want to, let me bring this one up. I don't want to get a little bit confused, because here, when we say x minus c greater than delta, less than delta, and greater than, this means greater than 0. Because we are used to that, we are used to this notation to think about negative. So absolute value cannot be negative. That means should be greater than 0. And the reason for that is the definition of absolute value. Let me go over that. So this one you are comfortable, huh? Let me go over why puts it greater than 0. That comes from definition of absolute value. Now, what is definition of absolute value from grade school? Excuse me, from basic algebra. Absolute value of x is greater than. If x is greater than or equal to 0, then what? Then absolute value of x is x. Greater than or equal to 0. So if we take away the equality, that means we are dealing with those numbers that are greater than 0. Now, you remember the sign this one, it just take this one and flip it over. Take this one, flip it over. Then again the positive stays same. So let me do it, huh? Now look at that. Look at that. Absolute value of x, here is absolute value of x is greater than 0. So this means same. Absolute value of x is greater than 0. So don't think that stands for what? For negative. That doesn't, the absolute value cannot be negative. Do you follow that? A kind of mirror image. This is mirror image of that, in fact. So you put something in front of the mirror, you don't, the object is not changed. Okay, now let me go. Okay, I'm giving some more talk about the basic algebra meaning of absolute value so that we are more comfortable to comprehend the abstract definition. Now, absolute value of x minus a less than 2, we are familiar with that. We write it, we surround it between 2 and minus 2, and we take the x minus a out of the GL of absolute value. And here then we add to both sides, very simple algebraic manipulation to minus plus a to both sides, and we end up to this expression. That means all the values between a plus 2 and a minus 2. So a is the center, geometrically a is the center, and a plus 2 is the right side of the interval, and a minus 2 is left side of the interval. And what is the length of this interval? To the right is plus 2, to the left of minus 2. So the length of that is 4 units. 2 and 2 is 4 units. That's very important to see. We will see it when we go to delta part of it. If we write it in the into interval notation, we write a minus 2 comma a plus 2. That's geometrical representation. This is analytical representation of what? Of this impression, which is from basic algebra. Now we can apply this one to this. So x minus c less than delta, delta is a positive number, greater than 0 means what? Means this. The only difference is that here x cannot assume the value of c, can assume all the value in its neighborhood, but not the value of c. You follow me? That's what it means. So if you write it in a interval notation, you have to mention that x is not equal to c. You see here I say x is between this and this, but I did mention that x is not equal to c, and that is the geometrical representation of this. But here I put c here, which means what? Here, let me even put it here. Means c cannot be what? Cannot be the c. I put it here, and I put a hole there, which means x cannot assume the value of c. Okay, so far so good. Okay, next is this one. We worked with that with the number 2 from basic algebra. Now we want to do exactly the same thing with delta, because in our definition we are dealing with Epsilon-delta. Now look at this one. I say x minus c less than delta greater than 0. We know why it's not greater than 0. Why? We have to put this notation, this symbol. This means x, again I'm repeating myself for the third or fourth time, x cannot assume the value of c. Because if x equal to c, then that will be 0. You follow me? And it says in the limit process we are approaching to c but not equal to c. Now here, this is delta means what? From c to c plus delta and c minus delta means the length of this interval is 2 delta. 2 delta, not 1 delta. So from the center to here is 1 delta, from here to here is another delta. You see that? So when we say this less than delta, we means what? We means this delta to the right and this delta to the left. Do you follow me? It doesn't say 2 delta. So our delta is this. We will come to that when we, for much further for this one. Now the very same is true when we talk about epsilon. So you can take a notes if you want. You have lots of time to take notes because you have upper hand with your computer to pause and take notes if you like to do so. If it is in live class, of course I will be giving them time to take notes if they like to do so. Okay, the very same is true with this one. F of x minus L, absolute value less than epsilon, he doesn't say it's greater than 0. That means what? We are coming to that. Why it doesn't say that? We haven't answered that question yet. No, this means this. You see that? L is the center, then epsilon more, epsilon less. So we can say epsilon tolerance of L. Epsilon tolerance. Okay, now let me go to some more geometry for the application of epsilon and delta. Geometrically, before I go to analytical approach of it. Now, here, let's talk about our graph. Remember the graph of, we covered about x squared minus 4 over x minus 2, that was our f of x, as x approaches to 2. Let's say c's are 2, all right? Now, that was a line, g of x was x plus 2. Let's assume that is x plus 2. Now, look, give me an epsilon. Epsilon is arbitrarily, most of the time is very small. But give me an epsilon, then I can determine a delta for you. Look at this, I'm determining that one geometrically. So what I did, I reflected that one, and it came to the x-axis here, I end up with that one. Okay, my delta will be from C to C plus delta, and C minus delta. You see that, the red part here? That is my delta, geometrically. You see that? I reflected and I found my delta. So you gave me epsilon, I did find you for delta. Now, for every x, every value that x can assume in this interval from negative delta to positive delta, or from this delta to this delta, two deltas, any value x assumed, the function taking those values will land 100% within this L plus 1 and L minus 1 interval, 100%. If it didn't happen, then we have made something wrong. You will see that analytically. So this is one. Now the other one is that to say, okay, this is linear. Now one thing we notice, by the way, this is a good thing to notice. This, the interval that I already covered, the L is always symmetry. Let me put that one up one more time. You see that? The interval L is always in between, center between L plus epsilon and L minus epsilon. You see that? And the one that we just went over, the geometrically here, because the graph is a linear, so C end up to be also center of between what? Between C plus delta and C minus delta. But that is only if the graph is linear. If the graph is not linear, that most of the time that is the case, is a curve, then this delta, we will have a bit difficulty. Geometrically, we will have difficulty, and also analytically, we will have difficulty with that. We have to select, we have to make our selection. So we will see that one. Let me hang that one up for you. So you see what I'm talking about, huh? If it is linear, C will be center. The L is center, C will be center between C plus delta and C minus delta. But if it is a curve, then C will not be center. This is always center. L is always center between L plus delta and L minus delta, because that's what we select. Let me see if I have one. Let me talk about that before I hang the other one up for you. So you're comfortable with this, hopefully. All right, Rabbit. Okay, now look at this one. Here, we are approaching, we want to see the limit. We approach from the right, the function has value. We approach to the left, the function has value. Okay, give me an epsilon, whatever you want. And the limit from the right is 5. The limit from the left is 2. You can see that, huh? Give me an epsilon so that I can see, I can find for you a delta. You give me a little epsilon, 5 plus epsilon, let's say 0.1, 0.2, 0.01, 1, whatever you select. Let's say epsilon is 1. If epsilon is 1, then that is 6. Then the other one will be 5 minus 1, which is 4. But look at that, there is nothing here. The function has no value. You see that? There is a gap, there is empty set. You see that? 5 minus epsilon, there is nothing here, so that I can see what is the value of function. So that is the reason symmetry is important. You say L plus epsilon, L minus epsilon. When I get L minus epsilon land here, and between these two, there is nothing there. There is no function, the value of function. So I cannot talk about delta epsilon or epsilon delta definition of limit for this particular example. You follow me? Okay, this is a good observation also to make. So how important delta epsilon is, and how fascinating the Weierstrass came with that very good, beautiful definition of the epsilon delta definition of limit. Now, let me center this one. Now, in this example, my graph is not linear, it's a curve. Now, look what happens. I want to see what is the limit as x approaches c from right hand side, geometrically. So I give the epsilon, L plus epsilon, L minus epsilon. I repeat myself. This is always symmetry. So I project it to here, and I project it to here, and look what happened. C is not in the center. C is far away from this point and closer to this point. So I have two deltas here to select. There are two candidates for delta. One of them is delta 2, which is much larger interval, as you can see, and the other one is delta 1, which is smaller than delta 2. Which one of them should I select? Now, suppose I select delta 2. If I select delta 2, all the elements from delta 2 to the right of C and delta 2 to the left of C, they must land, when function takes those values, they must land within what? Within this L plus epsilon, L minus epsilon delta, what is it, interval. But look at that. I have no problem here, anything, because it's reflection from that. Everything I take here will land here. You see that? Land here. But if this is my delta, is delta to the right and delta to the left. So delta to the left will be here. Look at that. When I take this one to the other side, it will be far, far. I put a point here. I don't know if I have, maybe I can put a line on that. Look at that. If this is my delta, if I select delta to be my delta, and to the right is delta, to the left will be this line. You see that? And in here, the function has no value, because the graph shows from this point to this point. You follow? So my selection of selecting delta to be delta 2 was not good. So what about delta 1, which is the smaller of the two? When I take delta 1, then I delta 1 to this side, and what is the other one? Delta 2. If I go to the left of that, it will be again will follow. Because if this is delta 1, now look at this one. I go to the right. Let me graph that one. Same distance. Let's say delta 1 is the interval is this much, and I go up. Now look happens. Everything in this interval, everything, all the x's, the f can take those values and map them into between what? Between L plus epsilon and L minus epsilon interval. 100%. Every value in here will land here, but every value in delta 2 did not happen for the selection of delta to be delta 2. So in this case, the smaller of the two is the right choice. And once it works for L delta 2, in case, delta 1, which is smaller than delta 2, then any other delta smaller than will work naturally. So hopefully you are comfortable with that graphically, because this visual aid is very important for comprehending the concept when we go to analytical approach. Analytical approach, we don't have picture. We have algebraic approach, so we don't have picture. So we have a picture, we have the idea, so we can select. If that didn't happen, how can we make sure that our selected delta is the right delta? if we have more than one, if we have a candidate of 2 deltas. Okay, then take a note out of it if you wish, and I go to the next one. So hopefully right now you have got pretty good idea about delta epsilon definition of limit, what it means, and geometrically. And now let's go to our question that we asked in the beginning. I have written that one here, just if you like to take a note or something. So two curious questions that I asked. One of them was what? One of them was that why you put 0, you put greater than 0, why not without that? We answered that one. I don't have to go through that. And the second one, why didn't you put greater than 0 here? You put for here, for delta, but you didn't put for f of x minus L less than epsilon for this absolute value. So we go for that one and try to answer that one. Now let me see if I have it. Yes, I do. You got the question, huh? Just curiosity. Curiosity killed the cat. But in the science, curiosity make Einstein. So we are not cats, huh? Only cats can die for being curious. Curiosity can only kill cats. Okay, and rabbits. Okay, now here we put greater than 0 and look what happens. If this is greater than 0, if you remember the example that we have was x squared minus 4 over x minus 2, that was our what? Our f of x. We took the limit of that, ended up to be 4. So the x can never assume 2, and f of x, the value of that can never assume 4 also. It's just closer and closer, but never become 4, because x never become 2. Now, if I put greater than 0 here, that means f of x can never get the value of 4. You can see that, huh? Because if you get the value of 4, you get what? You get 0. If I write like that, means f of x can get the value of 4. But if I write greater than 0, means f of x cannot get the value of 4. Now look what happened. When I cancel x minus 2 of numerator, x minus 2 over denominator, I end up with another function, which was g of x. G of x equal to x plus what? X plus 2. Now look what happened. Limit of this one, they both had the same limit, you remember? Limit of this one, as x approaches from right hand side and left hand side, equals to 4, but the value of the function is also 4. You see that? If you put 2 for here, because x approaching 2, you put 2 for x, you get 4. So g of x is perfectly defined at x equal to 2. G of x is. F of x was not, but g of x is. So if I put greater than 0, that means g of x will not have its limit, which means no graph will be, every graph will be dot and space, and dot and space, which means there is a hole on the graph everywhere, because the graph is not assuming or assuming its limit. So that brings difficulty with continuity. That means the graph of the function cannot be continuous. That is the reason we don't put this one here. So we say what? We say f of x minus is greater than epsilon, but we don't put this one here. All right? Just excuse me, I say greater than epsilon. Less than epsilon, but not greater than 0. Which means f of x can assume the value of 4. And in this case, it does, in fact. All right, now let me see. I have talked about this one. I don't think I need to. Well, I put this one for you if you like to write. I pause for a few seconds. What I just said, I have put it in writing for you, for those that they like to take notes. So let me put this one up and I'll hold it for a few seconds. You can pause your computer and write the notes if you want. I just mentioned it orally. What I just said, I have put it in writing. All right? 1001, 1002, 1003, sufficient. All right, Rabbit. Now, I guess we have answered all the questions. and hopefully the abstract part of the epsilon delta definition of limit has already been kind of filtered away, hopefully. But when we go to related theorems and some problem we solve analytically, we will see that we see this definition in application, and then after few problems, then hopefully will be once and for all the abstract of the definition of epsilon delta definition of limit will be filtered away. And as I already mentioned, it's very, very appealing and nice and interesting definition. Okay, then I thank you for watching. I will be giving more lectures. I will be going through some theorems to prove and some examples, and 2 or 3 maybe more videos, and we are done with this topic of epsilon delta definition of limit. All right, then I thank you all for watching. I wish you prosperity and good health, and please stay safe. So long.